The component method of vector addition involves a little bit of trigonometry and a methodical system for accounting for the x and y components of each vector. First, let's remember that a vector is a quantity that has both direction and magnitude. We use arrows to represent both the magnitude and the direction, the length of the arrow being the magnitude and the head of the arrow pointing in the direction. To determine the angle of a vector, we will use universal direction, meaning we will count counterclockwise from due east, representing 0 degrees, such that north is 90 degrees, west is 180 degrees, and south is 270 degrees. The magnitude of a vector in a scaled vector diagram is depicted by the length of the arrow. The arrow is drawn to a precise length according to the chosen scale. This is something we'll do when we start adding vectors graphically and we're using rulers, protractors, and graph paper. For now, we want to know how to do this mathematically. We want to separate the vector into its horizontal and vertical components. In this first example, the vector is on the x-axis pointing to the left, which corresponds with an angle length of 180 degrees. We will take the cosine and sine of this angle times the magnitude for the x and y components. The cosine of 180 degrees times 10 equals negative 10, which makes sense since an arrow pointing to the left is in the negative x part of the quadrant system. The sine of 180 degrees is 0, so our y component is 0, also making sense since a horizontal line has nothing vertical about it. Now let's do the second example. We have a vector with a magnitude of 20 meters at 30 degrees above the horizontal. We will resolve the horizontal component by taking 20 meters times the cosine of 30 degrees, which gives us 17.3 meters as the horizontal component. For the y component, we'll take 20 meters times the sine of 30 degrees, which equals 10 meters. This is how to resolve the x and y components of a single vector. Next, we need to explore what to do when there are multiple vectors so that we can find the magnitude and direction of the resulting vector. To resolve vectors by the component method, we will use the wrapped system. First, we will resolve the x and y components. Next, we will add these together for each x and y. Next, we will use the Pythagorean theorem to determine the magnitude of the resultant. And finally, to determine the angle, we will use the tangent of theta. This example says a cab driver is lost. First he drives 8 kilometers east, then turns and travels 10 kilometers south. Finally, he turns again and travels 10 kilometers at 30 degrees south of east to his destination. Solve mathematically. So first we will need to write out for each vector horizontal x and vertical y components. I like to make a chart. First, I'll list the magnitudes and the angle degrees for each one. Notice that for the x components I'm using cosine, for the y components I'm using sine. Due east corresponds with a universal angle of 0 degrees. Next we'll do 10 kilometers south. South corresponds with 270 degrees. The last one, 30 degrees south of east, would correspond to the universal direction of 360 degrees, which is counterclockwise around from the x-axis, minus those 30 for 330 degrees. Now that I've set up all three vectors by their x and y components, I'll do the math and then I can add all of the answers. This will cover the R part, resolve, and then the add part of our system. The sum of the x components is 18.4 kilometers. The sum of the y components is negative 16 kilometers. Next, we want to use Pythagorean theorem to find the magnitude of the resultant, which is 24.4 kilometers. And then finally, we'll do the tangent to get the angle. Technically, since we want theta, we will do the inverse tangent of x over y to determine the angle of the resultant. Be sure not to drop the sign because that'll affect your final answer. Let's work another example using the wrapped method. For the vector of 10 kilometers north, we'll take the cosine of 90 degrees for the x component and the sine of 90 degrees times the magnitude for the y component. For the vector heading due west, we'll do the same, but we'll use 180 degrees to represent west. The sum of the x components is negative 5 kilometers. The sum of the y components is 10 kilometers. We will now use these two values to figure out the magnitude and direction of the resultant vector using Pythagorean theorem and then the tangent of the angle. The magnitude will be 11.2 kilometers. For the direction of the resultant, we will take the inverse tangent of x over y. Use your calculator to find the answer. Now for one final example. We have three vectors, one heading north, one heading west, another heading north, and a fourth one heading east again. We know that north will be 90 degrees. We know that west will be 180 degrees. For each x component, we will use cosine. For each y component, we will use sine. Now north again, still 90 degrees regardless of the previous vectors. And then lastly east, which represents 0 degrees. Now we just need to do the math and add them together. The horizontal component is going to be 2.5 centimeters. The vertical component is going to be 5 centimeters. So we've done R and A. Now for P, to find C, we need the square root of the x component squared plus the y component squared, which will be 5.6 centimeters. And then lastly, to find theta, we will take the inverse tangent of x over y. Just remember RAPT. Resolve, add, Pythagorean tangent.